Next is the comparison of the reactivities of different carboxylic acid derivatives. This is the general formula of a carboxylic acid derivative where Z equal to X for acid halide, Z equal to OCOR for acid anhydride, Z is equal to NH2 for amide, and Z equal to OR for ester. Here, the carbonyl group in the carboxylic acid derivative is polar, which means a partial positive charge on its carbon and partial negative charge on oxygen, which means carbon atom is in electrophilic site. In other words, nucleophiles prefer to attack on this carbonyl carbon site. Therefore, when a nucleophile attacks a carboxylic acid derivative, a reaction can occur in which nucleophile replaces the leaving group. Consider the reaction. Here, it is the generalized formula of an carboxylic acid derivative. When it is attacked by a nucleophile, double bond will shift to oxygen. Then this negative charge retain its position. Z group will getting eliminated, and we get a product like this RC double bond O nucleophile plus Z minus. This type of reaction is called nucleophilic acyl substitution reaction. Here, when nucleophile attacks on this carbonyl carbon, first it will converted into a tetrahedral intermediate. That is tetrahedral alkoxide ion intermediate, followed by the elimination of Z, we get this product. This is the mechanism, general mechanism of nucleophilic acyl substitution reaction. Then what will be the order of reactivity of the four different types of carboxylic acid derivatives? That is, one is amide, ester, acid anhydride, and acid halide, which will be more reactive towards nucleophilic acyl substitution reactions. Here, in the nucleophilic acyl substitution reactions of these carboxylic acid derivatives, Z is the leaving group in general case. For amide, Z is NH2 minus, ester OR minus, for anhydride RCOO minus, and for acid halide X minus are the Z group, that is our leaving group, and these are Lewis bases. Then the order of basicity of these anions is NH2 is more NH2 minus is more basic than OR minus, which is more basic than RCOO minus, and which is more basic than X minus. This is the basicity order. And the above order can be used to explain the reactivity order on the basis of the two different factors, in which first one is resonance. In each carboxylic acid derivatives, the Z group, that is our leaving group, possess at least one lone pair of electrons. Hence, three resonance structures can be drawn for RCO set. That is the generalized formula of carboxylic acid derivative. In the first one, double bond will shift to oxygen and positive charge for carbon and negative charge for oxygen. When the lone pair of electrons present in leaving group set, it will donate to carbon and the single bond will changes into double bond and set, leaving group getting positively charged. These are the three resonance structures of carboxylic acid derivative. In structure 2, there is a positive charge on carbon, which makes it electrophilic and thereby prone to attack by a nucleophile. In structure 3, there is a positive charge on Z, resulting from the donation of its lone pair towards sharing. Then the basicity of Z determines how much the structure 3 would contribute to the resonance hybrid and how much electrophilic the carbonyl carbon would be. If basicity of Z is lower, which means its donation capacity will be lower, which causes the lower contribution of structure 3 to the hybrid and greater is the electrophilicity of the carbonyl carbon. If the Z group is weaker base means the lone pair of electron donating capacity will be lower. Then this carbonyl carbon will be more electrophilic and this resonance stabilization will be less. So, for weaker base, lower is the resonance stabilization, and for weaker base, the greater is the reactivity of the molecule towards nucleophiles. Then from the first argument, that is, if the basicity of Z is lower, resonance stabilization will be lower, which means stability order of the molecule would be amide is greater than ester, which is also greater than anhydride, which is also greater than acid halide. And from the second argument, that is lower the basicity, greater is the reactivity of a molecule towards nucleophile. We can say that the reactivity order would be acid halide is greater than anhydride, which is greater than ester, which is greater than amide. And second factor is leaving group ability. The weaker the base, the better is its leaving group ability, because the easier it is to eliminate in second step of the mechanism, which means the leaving group ability varies as X minus greater than RCO minus, which is greater than OR minus, which is greater than NH2 minus. That is, NH2 minus is the least leaving group able group. This leads to the following reactivity order in step 2. That is, acid halide is more reactive than acid anhydride, which is more reactive than ester, and which is more reactive than amide. Then by combining these two factors, one is resonance factor and another one is leaving group ability factor, together we can say the order of reactivity towards nucleophilic acyl substitution is acid halide is more reactive than acid anhydride, and which is more reactive than ester, and which is more reactive than amide. That is the order of reactivity in the case of different carboxylic acid derivatives.